There's DC current and AC current together, and the polarized domains in fact cause that there's non-zero Z component, the longitudinal component of the magnetization, derivative of this component, type of derivative. Let's go to the sensor itself. We used the ribbon with this composition, anealed at under 50 megapascals and 100 megapascals. So the sensor itself is very easy. There is only a ribbon and the pickup coil. And for these conditions, 200 kilohertz, 10 milliamps RMS sine wave signal, and for DC current from 0 up to 10 milliamps, we observed those responses. As I said before, for 0 DC bias field, DC bias current, there shouldn't be any response in the pickup coil, but there was remaining some helical anisotropy, as we think, in the ribbon, and therefore there was appearance of some pickup voltage in the coil. But when we apply DC bias current, then the characteristic changed to the antisymmetrical one with significant quasi-linear part. Moreover, when we here you can see this one ribbon annealed for 100 megapascal, which is the response is the blue one, and the other ribbon was annealed under 50 megapascal, and the response is the black one. The higher the tensile stress applied during the annealing, the larger is the anisotropy field induced, and wider is the quasi-linear part of the response. As most of the presenters here, I made some noise measurement as well. And here is one example of screenshot from the analyzer for 800 kilohertz, 10 milliamps RMS sine wave signal with DC bias of 10 milliamps. The PSD for 1 hertz, at 1 hertz is 17 picotesla, and RMS noise in the band from 10 millihertz to 10 hertz, so in the black region, was 240 picotesla. Here are, I made more, more measurements regarding the noise parameters. Here you can see the frequency dependence of the sensitivity, which is the red one and the red axis, and with relation also to the noise, the RMS noise in the band of 10 millihertz to 10 hertz band. So you can see that there is some maximum in sensitivity, and it is for 50 megapascal annealed ribbon. Okay. The other figure shows also dependence of sensitivity and RMS noise, but dependence to the DC bias, as it was mentioned on Monday. If you apply a little bit of DC bias current, you improve the noise stability, and we cannot work without DC bias current. And here you can see that for almost 300 kilohertz excited ribbon, and for 600 kilohertz ribbon, increasing the DC bias current, the noise level is going down. Last two slides. We made a very simple prototype of magnetometer using the sensors. You can see on as I said, it's simple. There is some excitation, pickup coil which serves also as a feedback coil, and synchronous demodulation, a feedback resistor, and going back to the feedback coil, pickup coil. The magnetometer worked at 290 kilohertz, 3 milliamps RMS, sine wave, and 5 milliamps of DC bias. You can see here some responses for this magnetometer. And very last slide, instead of conclusion, I have results we achieved with such magnetometer. The most crucial is not the noise. Definitely we can improve the noise, but we have the crucial one parameter, which is the temperature stability, temperature offset drift of the material itself, not only magnetometer. It's still huge. You can see. Sorry, this is the very last slide.